energy and momentum are independent conserved quantities. They follow different rules and serve for different reasons. And knowing one doesn't tell you the other. This should bother you. If you think of momentum as the amount of motion, then how can you lose half the motion energy but keep all the momentum? What kind of amount of motion is that? Let me make this sharper with a specific example. Take a 5-kilogram ball moving to the right at 4 meters per second. 5-kilogram ball sitting still. The first ball stops dead, and the second ball takes off at 4 meters per second. Momentum before 20 kilogram meters per second. Momentum after 20 kilogram meters per second. Energy after 40 meters. Everything is conserved. Clean and tight. But now change the collision. Make the balls sticky. They collide and stick together. One 10-kilogram lump moving to the right. By conservation of momentum, the combined lump must have 20 of momentum. 10 kilograms times what velocity? 2 meters per second. The lump is going half as fast as the original ball. So what's the kinetic energy after? 1/2 times 10 times 2 squared. That's 20 joules. We started with 40. Half the kinetic energy just vanished. Poof. Gone into heat and sound and deformation. But the momentum is exactly the same. 20 before, 20 after. So energy and momentum can behave completely differently in the same event. One gets halved while the other is perfectly preserved. That tells you they're measuring fundamentally different things. Momentum is not energy's cousin. It's not a slightly different flavor of how much motion. It's tracking something else entirely. Something independent. Something with its own reason for existing. And the reason it's not adding up with the simple picture is that our picture of momentum is too simple. It's too narrow. It's a cartoon version of something much more interesting. So, let me take you somewhere unexpected. I need to take you into empty space. Not outer space. Not stars and galaxies. I mean the space around you right now. The emptiness between objects. The stage on which everything happens. Because the secret of momentum is not about objects at all. It's about space itself. Pick a spot. Any spot, call it here. Now pick another spot 5 meters to the left. Call it there. Now let me ask you a strange question. Is here any different from there? I don't mean is the furniture different. I don't mean is the temperature different. I mean are the fundamental laws of physics different at here compared to there? If you set up an experiment here, measure everything carefully, record the results, then pick up your entire laboratory, every atom of it, move it 5 meters, set it down and run the exact same experiment. Do you get the same result? The answer is yes, you do. Every experiment ever conducted confirms this. The laws of physics don't depend on where you are. They are the same here as there, the same in New York as in Tokyo, the same in this room as on the surface of Mars, the same in this galaxy as in a galaxy 10 billion light years away. Now this sounds obvious, almost too obvious to be interesting. Of course the laws are the same everywhere. Why wouldn't they be? But stop. It is not obvious at all. The universe could have been set up different. Gravity could have been stronger in one corner of the room. Electricity could have worked by different rules on the north side of the lab compared to the south. The speed of light could have been different in different regions of space. It could have been a patchwork quilt of different physics in every neighborhood. It isn't the space is uniform, homogeneous, the same everywhere. And we've checked this, not casually, obsessively. Astronomers look at galaxies billions of light years away, and the light coming from those galaxies is produced by the same atomic processes that happen in labs on Earth. The spectral lines of hydrogen in a galaxy 10 billion light years away match the spectral lines of hydrogen in a tube in a university basement. Same physics, same rules, across unimaginable distances, across billions of years of cosmic time. Physicists call this property translational symmetry. If you translate meaning shift, your entire experiment from one location to another, nothing changes. The outcome is identical, and this has been verified to extraordinary precision. Nobody has ever found a crack. Nobody has ever discovered a place where the rules are different. This uniformity of space is one of the deepest facts about the universe we live in. It is not a consequence of some other law. It is not derived from anything more basic. It just is, and it has consequences that are staggering. In 1915, mathematician named Emmy Noether proved something extraordinary. She proved a theorem. Not a conjecture, not a guess, a mathematical theorem, airtight and irrefutable. Noether was working at the University of Göttingen, and she wasn't even allowed to hold a proper faculty position because she was a woman. She lectured under other people's names, she was paid almost nothing, and yet she produced what many physicists consider the single most important theorem connecting mathematics to physics. It says every continuous symmetry of the laws of physics corresponds to a conserved quantity. For every symmetry, there is something that cannot be created or destroyed. Let me be precise. A continuous symmetry means a transformation you can do by any amount. You can shift your lab 1 meter, or 2 meters, or half a meter, or a tenth of a millimeter. Any amount. That's a continuous symmetry, as opposed to a discrete symmetry like flipping left and right. Noether's theorem says find a continuous symmetry, and I will hand you a conservation law. Guaranteed. No exceptions. And it works backward too. Find a conservation law, and I will find you a symmetry. Let me give you an analogy that might help this land. Imagine a perfectly flat, featureless ice rink that extends infinitely in every direction. You're standing on it. No friction. You push a puck. It slides away forever in a straight line at constant speed. Now here's the key. Because the ice is the same everywhere, it doesn't matter where you push the puck. Push it from the center. Push it from the far corner. Push it from any spot at all. Same push, same result. The puck doesn't care where it started. That's spatial symmetry. Now imagine the ice has a hill in the middle, a bump. Suddenly, it matters where you push the puck. Push it on the flat part, and it slides away cleanly. Push it near the bump, and it curves, or slows, or speeds up. The result depends on location. Spatial symmetry is broken. And guess what? On that bumpy rink, momentum is not conserved. The bump can absorb momentum or inject it. The puck can speed up going downhill and slow down going uphill, even with no outside push. The total momentum of the puck changes because space is not uniform. This is not just an analogy. This is exactly what happens with gravity. A ball falling toward the earth is gaining momentum. Where does that momentum come from? From the gravitational field. From the fact that space near the earth is not the same as space far from you. The symmetry is broken. And so momentum of the ball alone is not conserved. You have to include the earth and its field in the accounting. When you include everything, the symmetry is restored, and the total momentum of ball plus earth is conserved again. So Noether's theorem doesn't just tell you that momentum is conserved. It tells you precisely when and why it would fail to be conserved when the symmetry is broken. That's an enormously powerful diagnostic tool. And here's the punchline. The translational symmetry of space, the fact that the laws of physics are the same at every location, corresponds to the conservation of momentum. That is why momentum is conserved. Not because of some property of collisions, not because of some accounting trick with mass and velocity. Momentum is conserved because space is uniform. Take a moment with that. The reason a billiard ball transfers momentum to another billiard ball is that the laws of physics don't change as you move from one place to another. The reason a rocket works, the reason an explosion conserves momentum, the reason every collision in the history of the universe has balanced its momentum books, is that space looks the same here as it does 5 meters to the left. That is the deep reason, the real reason. Everything else is a consequence. And if it didn't stop there, her theorem gives us more. The fact that the laws of physics are the same today as they were yesterday, that's time symmetry. And time symmetry gives us conservation of energy. The fact that the laws of physics don't change when you rotate your lab, face it east instead of north, that's rotational symmetry. And rotational symmetry gives us conservation of angular momentum. 3 symmetries, 3 conservation laws. Space uniformity gives momentum. Time uniformity gives energy. Rotational uniformity gives angular momentum. The 3 most important conservation laws in all of physics, and they come from the 3 most basic symmetries of the universe. That's not a coincidence. That's the structure of reality. And it keeps going. In particle physics, there are more exotic symmetries, internal symmetries having to do with the way particles transform under the forces of nature. And each of those symmetries gives its own conserved quantity. Conservation of electric charge comes from a symmetry. Conservation of a quantity called baryon number comes from a symmetry. Every conservation law you've ever heard of, and several you haven't, traces back to a symmetry through Neither's theorem. It is the master key that unlocks the entire cabinet of conservation laws. And here is why the clay collision makes sense now. Remember, two lumps of clay slammed together, kinetic energy is lost, but momentum is conserved. Earlier that seemed contradictory. How can you lose one measure of motion but keep the other? The answer is that energy and momentum come from different symmetries. Energy comes from time symmetry. Momentum comes from space symmetry. They're independent. Losing kinetic energy in a collision doesn't violate time symmetry because the energy didn't vanish. It turned into heat and sound and deformation. Total energy, including the thermal energy, is still conserved. And the collision doesn't violate spatial symmetry at all, so momentum is perfectly conserved in its visible mechanical form. They're separate books kept by separate accountants for separate reasons. Once you see this, the whole landscape of physics reorganizes in your mind. And now let me go further. Let me show you what momentum looks like in quantum mechanics, because this is where the old picture really falls apart. In quantum mechanics, particles don't have definite positions. You've heard this before. An electron is not a little ball sitting at a specific spot. It's described by a wave function, a mathematical object spread out across space. This wave function tells you the probability of finding the electron in various places if you go looking for it. It's a cloud of possibility. And here's the remarkable thing. The momentum of a quantum particle is not mass times velocity. You cannot even define velocity in the usual way for a quantum particle because it doesn't have a definite position moment to moment. So how would you track how fast it's going from one spot to another? Instead, the momentum is determined by how the wave function changes across space. Specifically, it depends on the wavelength of the wave. Short wavelength, high momentum. Long wavelength, low momentum. Very tightly packed oscillations mean the particle is carrying a lot of momentum. Gentle, spread out waves mean very little momentum. Think of it like sound. A high-pitched note has a short wavelength. The air pressure oscillates rapidly from one point to the next. A low-pitched note has a long wavelength. Gentle, slow oscillations. The momentum of a quantum particle works the same way. A high-pitched wave function corresponds to high momentum. A low-pitched one corresponds to low momentum. The analogy isn't perfect, but it gives you the flavor. This is completely different from mass times velocity. There's no velocity in the picture at all. It's just a wave and how rapidly it oscillates from point to point. And yet it's the same momentum, the same conserved quantity. It obeys the same conservation laws. It transfers the same way in interactions. The definition changed, but the deep identity, the thing that Noether's theorem guarantees, stayed exactly the same. And from this quantum picture of momentum, you get something remarkable for free. The Heisenberg uncertainty principle. Listen to how naturally it falls out. If you want to know exactly where a particle is, you need its wave function to be concentrated in a very small region, squeezed into a tiny spike. But think of what happens when you squeeze a wave into a tiny space. To be confined to a small region, the wave function has to change very rapidly. It has to oscillate like crazy to fit into that small area. Rapid oscillation means short wavelength, and short wavelength means high momentum. More precisely, it means the particle could have high momentum or negative high momentum, because the wave has to have many different wavelengths mixed together to make that tight spike. So by pinning down the position, you've made the momentum completely uncertain. It could be anything. And it works the other way too. If you want a particle with very definite momentum, you need a nice clean wave with a single wavelength. But a single wavelength wave extends forever both directions. It's not localized at all, it's everywhere and nowhere. So you know the momentum precisely, but you have absolutely no idea where the particle is. That is the uncertainty principle. And notice there was no hand waving, no appeals to the act of measurement disturbs the particle, no philosophical mumbo-jumbo about consciousness or observance. It's just mathematics. It's just what happens when momentum is defined by the spatial structure of waves. The uncertainty principle is a direct mathematical, unavoidable consequence of what momentum really is. And this has real consequences, not just philosophical ones. The uncertainty principle, flowing directly from the nature of quantum momentum, explains why atoms don't collapse. Think about a hydrogen atom. One proton, one electron. The proton is positive, the electron is negative, and they attract each other. So why doesn't the electron just spiral into the proton and sit on top of it? In classical physics it should, but in quantum mechanics, if the electron's position is squeezed down to a very small region near the proton, its momentum becomes wildly uncertain. An uncertain momentum means the electron has a high average kinetic energy. The closer you push it, the more violently it jiggles. At some point, the kinetic energy from the jiggling balances the attractive energy from the electric force, and you get a stable atom, a specific size, a specific energy. The size of a hydrogen atom, about 500ths of a nanometer, is determined by this balance. And that balance exists because momentum in the quantum world is tied to spatial variation. Squeeze the space and you blow up the momentum. It's Noether's conserved quantity expressed through wave mechanics that holds matter together. That is staggering. The reason atoms have the sizes they do, the reason chemistry works, the reason solid objects are solid, traces back to what momentum really means. Now let me swing back to something more familiar. The second law. Everybody knows it as F equals ma. Force equals mass times acceleration. But Newton himself didn't write it that way. Newton's original formulation was, force is the rate of change of momentum with respect to time. And this matters more than you might think. Because F equals ma and force equals the rate of change of momentum are not the same statement. They look the same when the mass doesn't change. If an object has constant mass, then the rate of change of mass times velocity is just mass times the rate of change of velocity, which is mass times acceleration. Fine, you get F equals ma. But what if the mass changes? Think about a rocket. A rocket burns fuel. It ejects hot gas out the back at tremendous speed.
Circle. Anywhere. Doesn't matter where. New York. Tokyo. The moon. Andromeda Galaxy. Measure the circumference. Measure the diameter. Divide them. You get the same number. Always. Exactly. 3.14159. Pi. Nobody taught the circle this. Nobody programmed it. Nobody decided it. It just is. But here's the question that bothers me. Was that ratio always there, waiting to be discovered? Or did we invent it, make it up, create it? This sounds like philosophy. Useless philosophy. But it bothers me. A lot. Because mathematics feels real. Feels discovered. Not invented. Pi exists. Whether humans exist or not. Right? Or does it? I'm Richard Feynman. I use mathematics every day. My whole career. Equations. Calculations. Predictions. And I don't know if I'm discovering truths or inventing tools. This bothers me more than it should. Let me explain why. Take the number 2. The concept of two-ness. 2 apples. 2 electrons. 2 galaxies. 2 anything. Is 2 real? Does it exist independently, out there in the universe? Or is it just a human concept, a word we invented, a tool we created? Plato thought numbers are real, exist in some perfect realm, abstract, eternal, unchanging. We discover them, don't invent them. Mathematical Platonism. Numbers exist, mathematical objects exist, independent of humans, independent of the physical world, in their own realm. When you prove a theorem, you're discovering a truth. That was always true, always existed, you just found it. This feels right to me, sometimes, when I'm doing mathematics. Feels like I'm discovering something, not making it up. Pi was pi before humans existed, will be pi after humans are gone. The ratio is out there, real, objective, true. Triangles have angles summing to 180 degrees, always, everywhere. Nobody invented this, we discovered it. The Pythagorean theorem. A quadtree plus B quadtree equals sine C quadtree. True for right triangles. Always. Everywhere. Eternally. We didn't make this up. We found it. This suggests mathematics is discovered. Real. Objective. Platonic. But then I think about it more. And I'm not sure. Consider negative numbers. Do they exist? Really exist? You can't have negative apples. Can't have negative mass. Can't have negative distance. We invented negative numbers. For convenience. For solving equations, for bookkeeping, human creation, tool we made, or complex numbers, imaginary numbers. I equal sign friend minus 1. What does that mean physically? Square root of -1. Doesn't exist. Can't exist. Impossible. We made it up. Invented it. For solving equations. For mathematics. For convenience. But then complex numbers turn out to describe quantum mechanics. Describe wave functions. Describe reality. Perfectly. How? If we just invented them, why do they describe nature? This is the puzzle, the mystery, the thing that bothers me. Mathematics feels invented when we're creating it, feels discovered when we use it. Both, neither. I don't know. Let me give you more examples. Make this concrete. Euclidean geometry. Parallel lines never meet. Seems obvious. Seems true. Seems discovered. But then we invent non-Euclidean geometry. Parallel lines can meet, or diverge. Curved space. Different axioms. Just a game. Just playing with ideas. Just inventing new mathematics. Fun. Interesting. But not real. Until Einstein. General relativity. Curved space-time. Gravity. Real space is non-Euclidean. Actually curved. Really real. We invented non-Euclidean geometry as a game. Turned out to describe reality. How? If mathematics is invented, why does it describe nature? Why does nature care about our inventions? If mathematics is discovered, why can we invent new mathematics? Why do we have choices about axioms, about definitions? Both options have problems. Neither feels completely right. I remember learning mathematics, graduate school, different areas, algebra, analysis, topology, geometry. Some felt invented. Like games, playing with symbols, following rules we chose, creating structures, fun, interesting, but arbitrary. Others felt discovered, like physics, uncovering truths, finding patterns, learning what's real, inevitable, necessary, and I couldn't tell which was which. or if the distinction mattered. I remember talking with a mathematician, pure mathematician, brilliant guy, loved abstract algebra. I asked him, do you think groups exist, really exist, or are they just human constructs? Groups, abstract algebra, sets with operations, axioms, theorems, very abstract, very pure mathematics. He said, of course they exist. I study them, discover their properties, prove theorems about them. They're real. But you can't point to a group. I said, can't touch it, can't measure it. How is it real? Numbers are real. He said, geometric shapes are real. Why not groups? I don't know if numbers are real either. I told him. He looked at me like I was crazy. You're a physicist. You use mathematics constantly. How can you doubt it's real? I use it. Doesn't mean I understand what it is. Doesn't mean I know if it's real or invented. He thought about this. Smart guy. Really thought about it. Okay, he said. Let me ask you this. Before humans existed, was the number 7 prime? Good question. Really good question. Makes you think. I think so, I said. 7 has no divisors except 1, and itself. That's true regardless of whether anyone knows it, right? Exactly. So it's discovered, not invented. The primeness of 7 existed before we discovered it. But what does 7 mean without humans to count to 7? What does prime mean without anyone to define it? The relationship exists, he insisted. The mathematical structure, the pattern, that's real. That's what we discover. Maybe, I said. Or maybe we create the concept of number, then discover relationships within that concept. First step invented, second step discovered. That's just semantics, he said. The relationships are what matter. Those are real. Those are discovered. I wasn't sure. Still aren't. But he had a point. A good point. The relationships feel discovered, feel real, feel objective. Whether the objects themselves are real, numbers, groups, shapes, that's less clear. He didn't like that answer. Thought I was being difficult. Maybe I was, but I meant it. Still mean it. Here's another angle, another way to think about it. Mathematics is unreasonably effective. Wigner's phrase. Unreasonable effectiveness of mathematics in the natural sciences. We invent mathematics for pure reasons, abstract reasons, no physical motivation, just playing with ideas. Then physics discovers that mathematics describes nature perfectly. Exactly. Complex numbers describe quantum mechanics. Group theory describes particles. Differential geometry describes gravity. Topology describes quantum field theory. Why? How? We just made up these mathematical structures. Why do they fit reality? This suggests mathematics is discovered, not invented. Because how else would it fit nature so perfectly? Nature is mathematical. We're discovering the mathematics that's already there, built into reality. But wait, maybe we're selecting. Among all possible mathematics, we notice the parts that describe nature. Ignore the rest. Selection bias. We use what works, forget what doesn't. Makes it seem like mathematics is perfectly suited for physics. But really, we're just picking the useful parts. Maybe. I don't know. Both explanations feel incomplete. Let me give you a concrete example. From my own work. From physics. Quantum electrodynamics. QED. My Nobel Prize work uses complex numbers heavily.
QED.
Wave functions, amplitudes, phase factors, all complex. When I first learned this, I thought, complex numbers are just a mathematical trick. Convenience, not real, just a tool. Real measurements are real numbers. Probabilities, energies, positions, all real. So complex numbers are just intermediate steps. Bookkeeping, not fundamental. But then I studied deeper, worked more, and realized you can't avoid complex numbers in quantum mechanics. Not just convenient, necessary, essential, fundamental. Quantum mechanics without complex numbers, impossible. Doesn't work. Can't be formulated. Not just difficult, actually impossible. How? If complex numbers are invented, minus just human tools, how can nature require them? How can reality need imaginary numbers? This suggests they're discovered, real, part of the structure of reality. Not invented tools, but discovered truths. But I invented them. Humans invented them. To solve equations. For convenience, they're not real. Round and round. Same puzzle again, same confusion. I teach this to students. Quantum mechanics, complex amplitudes, phase factors. Students ask, what does the imaginary part mean physically? And I I say, nothing. It's not physical. It's mathematical. But you said it's essential, necessary. It is. The mathematics requires it. Nature requires it. Doesn't mean it's physical. It means it's mathematical. So mathematics is more fundamental than physics. I don't know. Maybe. Sometimes feels that way. This confuses students. Confuses me too. Still does. Let me tell you what I do know. What I'm sure of. Mathematics works. Whether invented or discovered, it works. Makes predictions. Solves problems. Describes nature. And that's what matters for physics. For science. For applications. But philosophically, I don't know what mathematics is. Where it comes from. Whether it's real or invented. And I've made peace with that. Mostly, I use mathematics.
Made peace with
Trust
it.
it. Rely on it. Every day. Without knowing what it fundamentally is. Like using language. I speak English. Don't know if words are real or invented. Doesn't matter for communication. Still works. Same with mathematics. Use it. Works. Don't need to understand its ontological status. But it still bothers me. Still fascinates me. Still makes me wonder. Because mathematics feels different from other human creations. Feels objective. Universal. True. You can't vote on whether pi is 3.14159. Can't decide by consensus. Can't change it by decree. It just is. That suggests it's discovered. Real. Objective. Independent. But we can invent new axioms. New systems. New mathematics. Make choices. Have creativity. Have freedom. That suggests it's invented. Created. Human-made. Dependent on us. Both seem true. Both can't be true. Or maybe both are true in different ways. I teach students mathematics. Show them equations, derivations, proofs. Sometimes I say, look what we discovered. Sometimes I say, here's what we invented. Depends on the topic. Depends on my mood. Depends on how it feels that day. Students ask, is this real? Does this exist? And I say, it works. That's what matters. Whether it's real is philosophy. Whether it works is physics. Not satisfying, but honest. Here's my best guess. My current thinking. Subject to change.
Current
Mathematics has
thinking.
two aspects. Two parts. One part is discovered. The relationships. The patterns. The structures. Pi being 3.14159. The Pythagorean theorem being true. These are discovered. They're real. Objective. True. Other part is invented. The notation. The axioms we choose. The definitions. The systems we build. These are created. Chosen. Human-made. Discovery and invention mixed together. Intertwined. Inseparable. We invent the framework. Discover the consequences. Create the axioms. Find the theorems. Make the rules. Learn what follows from them. Both. At once. Simultaneously. The circle ratio being pi. Discovered. That's real. That's out there. Calling it pi. Invented. Human choice. Could call it anything. Using base 10. Invented. Could use base 2. Or base 60. Human choice. But the mathematical relationships, those are discovered. Real. True regardless of notation or base or language. This is my best answer. The relationships are discovered. The representations are invented. Mathematics is the study of necessary relationships. If you have these axioms, these conclusions follow. Necessarily, inevitably. That necessity is discovered. Real. But which axioms to study? How to represent them? What notation to use? Those are invented. Chosen. Human decisions. So mathematics is both. Discovered relationships and invented frameworks. Real patterns described in human tools. This satisfies me. Sometimes. Other times I'm not sure again. Because even the axioms feel discovered sometimes. Like we're finding the right axioms, not just choosing arbitrary ones. Euclidean axioms feel natural, inevitable. Right, not arbitrary, but we can choose different ones. Non-Euclidean geometry, different axioms, also natural, also inevitable, also right. So maybe natural is just what we're used to, what fits our intuition, not what's discovered. I don't know. Round and round, never fully resolved. Here's what I tell students, what I've learned, what I believe. Mathematics is useful. Whether discovered or invented, it's useful, powerful, beautiful. Use it, study it, appreciate it. Don't worry too much about whether it's real. If it helps you understand nature, it's good enough. If it makes predictions that work, it's true enough. Philosophy can wait. Physics needs mathematics now. Use what